In this video, we're going to look at the central limit theorem. The central limit theorem says, regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases. So previously we've seen the theorem that if we know that the population's normal, then the sampling distribution of x bar will be normal as well. So contrasting that with the central limit theorem says that even if the underlying population's not normal, the sampling distribution of x bar becomes approximately normal as the sample size n increases. So if we have a relatively small sample size, if the population's not normal, then the sampling distribution of x bar won't be normal either. But if we have a large sample, then even if the population's not normal, the x bar distribution will become normal because the sample size is so large. So again, even if the population's not normal, the sampling distribution of x bar will be normal if the sample size is large enough. So as a rule of thumb, if the distribution of the population is unknown, or if it's known that the distribution of the population's not normal, then the distribution of the sample mean will be approximately normal, provided that the sample size is greater than or equal to 30. So our rule of thumb is going to be, as long as we're taking a sample of size 30 or larger, then we will be able to assume that the sampling distribution of x bar will be normal. Now again, keep it straight. There is an underlying population, and then there's a sampling distribution, right? So we're not saying the population's normal if the sample's 30 or bigger. We're saying that the sampling distribution of x bar will be normal if the sample size is 30 or bigger. Let's take a look at an example. So ATM withdrawals. According to Crown ATM Network, the mean ATM withdrawal is $67. Assume that the standard deviation for withdrawals is $35. We have three parts. Part A, do you think the variable ATM withdrawal is normally distributed? If not, what shape would you expect the variable to have? Part B, if a random sample of 50 ATM withdrawals is obtained, describe the sampling distribution of x bar, the mean withdrawal amount. And C, determine the probability of obtaining a sample mean withdrawal amount between $70 and $75. So, in this particular case, our variable is the ATM withdrawal amount. So what we're talking about is how much money an individual withdraws from an ATM, okay? And so we're told that the mean for ATM withdrawals, the mean amount is $67, and we're told that the standard deviation is $35. So in other words, we're told that the mean of the population is $67, and we're told that the standard deviation of the population is $35. What we're not told is whether or not the distribution of the population is normal. Okay, so it's not known. Okay, so in fact, that's what we're asked in Part A. Do you think the variable ATM withdrawal is normally distributed? If not, what shape would you expect the variable to have? Now, this is kind of an unfair question because, you know, how are we supposed to know without any data? How are we supposed to know whether this variable is normally distributed or not? But we can kind of use a little bit of logic and think about maybe our own habits. So again, the mean is $67. My thought is typically probably when a person goes to the ATM, they're not going to draw out $67. They're probably more likely going to draw out a lesser amount. So what I'm thinking is maybe it would be more likely that someone would draw out maybe $20 or $40. But then there would be a few maybe larger withdrawals that's going to pull up the average. So I'm kind of envisioning, and I don't really know because I don't have any data, but I'm kind of envisioning maybe a distribution that looks something like this, maybe a skewed right distribution. So again, most of the withdrawals maybe would be below $67, if say here's the $67, but there is a few larger withdrawals that's going to pull up the average. Okay, so do I think it's normally distributed? No, I don't think it's normally distributed. What shape do I think? I suspect it would be skewed right. But again, that's kind of an unfair question since we don't have any real data or anything to base that on. So I'm just speculating. B and C, though, I don't have to speculate on. If a random sample of 50 ATM withdrawals is obtained, describe the sampling distribution of X bar, and X bar is the mean withdrawal amount. So notice that our sample size in this particular case is 50. So N equals 50. Now when it says to describe the sampling distribution of X bar, what that really means is, can we say is it normal or not? So the fact that our sample size is 50, that's larger than 30. So the central limit theorem is going to apply. So we're going to be able to say that our sampling distribution is normal. Again, I know it's normal. Even though I don't think the population's normal, the sampling distribution is going to be normal because our sample size is large. It's bigger than 30, which was our rule of thumb. So the central limit theorem applies. Moreover, the mean of this sampling distribution of X bar is going to equal $67, the same as the mean of the population. And the standard deviation of the X bar distribution is going to equal our $35 divided by the square root of 50 because 50 is our sample size. So again, to describe the shape of the sampling distribution of X bar, I know that it's normal, I know the mean, and I know the standard deviation. Let me pull in my calculator here. If I take 35 divided by the square root of 50, then that is going to be approximately $4.95, but I'm going to carry out the decimal past 95 cents, so I'm going to say 4.949747. So approximately $4.95 would be the standard deviation for this sampling distribution. So in part C, determine the probability of obtaining a sample mean withdrawal amount between $70 and $75, and we're talking about for our sample of 50, so for this sampling distribution here. So we want to find the probability that our X bar is going to be between 70 and 75. So picture-wise, I have this X bar distribution. It's normally distributed. The mean is $67. Again, the standard deviation, 4.949747. So 70 is going to be around here. 75 is going to be around here. And I'm looking for that area in between. So I can determine this area by either doing it by hand with the normal table. I can use the normal CDF command on the calculator, or I could use the StatCrunch calculator. I'm going to use the TI calculator. So this is going to be normal CDF. My left bound is going to be 70. My right bound is going to be 75. The mean is 67, and the standard deviation is 4.949747. So if I bring back in my calculator, normal CDF, my left bound is 70, my right bound is 75, my mean again is 67, and my standard deviation is 949747. And so that gives me a probability of 0.1958. So if I randomly select 50 ATM withdrawals, there will be a probability of 0.1958 that the mean of those 50 withdrawals will be between $70 and $75. So again, we could do this problem by hand, or we could use the StatCrunch calculator. You're welcome to use those. In this video, I've just demonstrated using the TI calculator, but you can use any of those resources you feel like.